Hey class, this lecture is on the wave function, probability density, and Heisenberg's uncertainty principle. Definitely one of the strangest couple of concepts that we're going to learn since day one. And that's why we start off with this kind of TOK philosophical questions for a warm-up. Before I start, I do want to mention that there are 3 data booklet equations that show up. There are no sub-objectives that show up in the syllabus, but there are 3 data booklet equations you need to know, and so we'll be discussing these later. So the questions we have are, as humans, how do we know where something is? Like if there's a bird, like right here, there's a bird, how do we see that bird? The answer is pretty obvious, right? We have eyes, and we see the bird. This is at the macro level, macroscopic level. We're not going micro, we're not going quantum yet. But when we do, as scientists, how do we know where something we can't see is? Like if there's an electron, how do we know that it's right there? Right? We may have some sort of detector, right? Here, let's just make a detector, and we might be able to see it. But as we've learned previously, the electrons don't act fully as particles, they can act as waves. And so we're going to have to kind of combine these understandings of what does that mean? How can we measure, or how do we even measure the difference between electrons or quantum particles as waves or particles? So, right, this is the detecting screen that was seen in the Geiger-Marsden experiment. So we definitely use some sort of detector, right, and then we observe the detection. But those observations are like an endpoint. We're not observing the electron actually hit the screen. We just say, hey, electron has hit the screen here or around here. And so we aren't actually watching the electron travel to the screen. And that's a key part, is we don't really, it makes us aware of our incapability of observing quantum things happening. So similar to the standard model, the Feynman diagrams, we are only constructing like conventions for what occurs, and we are moving to a new convention of like what is the probability of something being somewhere, what does the wave function actually mean for a particle, and how does de Broglie's wavelength help us? And so we have to kind of combine all those together. So in 1926, Erwin Schrödinger looked at electrons inside of like the Bohr model, and determined that actually electrons do not orbit at specific energy levels because of this wave function, because of the electron's wave-like nature. And through some sort of mathematical understanding, which is slightly beyond me, came up with an equation to determine the probability of finding where a particle is. So we're going to move beyond this, though, and we're solely going to look at this wave function. I'm going to write this prettier. This is what we call our wave function. It's a symbol of our wave function. And this is what shows up in our data booklet. And we have this probability density function, which is the probability of finding a particle in a given volume, where this PR is, right, probability of finding a particle. Right, we have our wave function, which we just determined up here. And then this is like a given volume. But to be honest, if we simplify this down, and what you really need to know in IB physics, it's that the probability of finding anything is proportional to the wave function squared. That's like the big takeaway. So if anything, that's what you need to walk away with this. So we have an example. This is the probability distribution for hydrogen's 1s orbital. So this is like one electron existing inside of a hydrogen atom. There is a probability function for that electron, and this is what gives us those images of the electron clouds. And the question might be, where is the electron most likely to be? And you could identify and say, hey, right here. So at this point, at this distance r, we would most likely find our electron inside of our 1s orbital. And this is with a given graph of an electron in a 1s orbital, but there's times when we'll be looking at other graphs, or we'll be making the graphs, and although this has its problems, we can use our de Broglie wavelength for particles or ourselves. So remember back in matter waves and electron diffraction, we determined my wavelength and an electron's wavelength given some energy difference, some kinetic energy. And we found that we are off by an order of 10 to the 26th, which means I have a very, very small wavelength, whereas an electron has a, well, relatively larger wavelength than me. So if I were to kind of compare these two, I would see a wave packet for me that has very small wavelengths, and a wave packet for the electron that has much larger wavelengths. Of course, times 10 to the power of 26 should be, the ratio should be significantly larger than this, but we have to make do. And we said that the amplitude squared of our wave function, which is this is our wave function, if we are assuming that my de Broglie wavelength is my wave function, that's an assumption, then I know that I'm pretty much right there. There's, if I were to, this is me, there I am. But our electron is uncertain. We don't know exactly where it is. It's somewhere here. Like, where are you? So we can use this in a wave probability graph and determine the probability of finding it within a given position, but really knowing that this just shows that there's an uncertainty in position. But these electrons, these particles, are not standing still. So they're actually moving. And when they're moving, they end up having this, wave packet motion, and then there's this probability or uncertainty in position while moving. And this causes some interesting issues when it starts passing into an electric field or a potential difference, because normally we would say when there's an electric field, right, and the electric field is producing a force on the electron to oppose it, it should run into it and then, be pushed away, and it would travel backwards. And that is the exact same thing that we see with, us. What is our probability of running through a wall? 0. But actually, I have a probability, right? Here's my probability function. I have a chance of not being at my direct exact position. So, like, when you try to punch a wall, there is a very, 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 very small chance that your hand will go through the wall. But it's so small, it's negligible. And maybe one particle goes through the wall, but the trillions and trillions and trillions of other particles don't. So we just say pretty much, no, you don't go through the wall. Like, other forces are at play. It doesn't happen. But what's strange is when we try to pass an electron into, and now it's not a wall anymore. We're looking at, we call it a barrier, but the barrier means, like, this barrier pretty much means like a potential difference. And that is because there's a probability or an uncertainty in position, and there's a chance that it can pass through that barrier. So here's our electron wave function. It's passing through. It has a probability of existing somewhere. And as soon as it gets to the point where it's going to bounce off, or not bounce because it's producing a force, there is a chance that it can pass right through. And that's called quantum tunneling. The ability for something to pass through a potential barrier due to the uncertainty of the particle's position. And the factors that decrease the probability of quantum tunneling has to do with the strength of the potential difference, which is visually shown by the width or the height of this barrier, the mass of the particle, because that would affect the wave function, the de Broglie's wavelength, and the charge of a particle, because that would also affect the strength of the potential difference that they would have to overcome, the energy difference to overcome that. So when looking at a potential multiple choice problem for this, we would have a situation where the particle of fixed energy is close to a potential barrier, which changes to the width of the barrier and to the height of the barrier, will always make the tunneling probability greater. So the ability for it to tunnel through it, which means you need to decrease both the width and the height. So everything up to here has been pretty qualitative. We discussed that a particle's wave function, if we square it, it shows us the probability of finding it in a given position. We've looked at graphs that include this wave function. We've also identified de Broglie's wavelength as possibly being an approximation to a particle's wave function. And then we've said that in quantum tunneling, it has the ability to pass through due to the uncertainty of position, depending on how much potential it's trying to overcome, and of course, the qualities of the particle. But let's get into some math, which we're going to look at Heisenberg's uncertainty principle. And again, we're going to look at this from still a very simplified version of this. So Heisenberg's uncertainty principle states the position and momentum of a particle cannot be measured to infinite precision. The more precisely the position momentum of a particle is given, the less precisely can one say what its momentum position is. So in this diagram, we're kind of saying, hey, look, we have a large uncertainty of particles, and they're all going straight, which means the momentum is somewhat identified. It's precise. In the next one, as we decrease the position possibilities, decrease the uncertainty of that position, it's going to want to kind of diffract out like it did with light, right? Electrons as a wavelength will diffract through. And now it has an uncertainty in the momentum. This is shown in our single slit diffraction pattern for electrons, which also produced similar patterns as waves, as light. So we won't do the derivation to get to this, but we end up with these two strange equations where we have a first delta x, which is kind of the uncertainty of position. It also can be kind of referenced as the probability of finding something in a given position because that's kind of the same as the uncertainty. Delta P is the uncertainty of momentum. Now, with some finagling, you can actually determine that this equation is the same as also saying that the uncertainty in a particle's energy and the time that it has that uncertainty of energy also cannot be measured precisely. And this energy time uncertainty actually gives us support for what occurs during quantum particle interaction when there's a virtual particle. Because there must be some time duration, let's say right from here to here, in which a particle shows up. That particle has energy. So if this time duration is small enough, then there can be this fluctuation of energy that is large enough to produce a virtual particle. But due to the conservation of energy, it's only a fluctuation, it's only an uncertainty of energy, so it's going to be removed at some point in time to make sure the conservation of energy stands. So it's almost like this conservation of energy law is more at a macroscopic level, or maybe even a microscopic, but once you get to quantum, it breaks the conservation of energy for a small period of time. And when I say small, I say really small. So it's important to know that, though. This provides support for virtual particles. All right, so how can we apply this in given situations? I've got a fun example problem. In this example problem, we want to use the uncertainty principle to show that an electron cannot exist within an atomic nucleus. Now, sometimes they will give you the size of the nucleus, but if they don't, just assume that it's 1 × 10 to the negative 15th meters. And so that will be also helpful in some multiple choice problems when you have to do orders of magnitude. So if it's going to exist inside of here, then that's my probability position or my uncertainty of position. So delta x is equal to 1 times 10 to the negative 15th meters. It's important to note that even though we've used delta to signify like plus or minus values, in this case it's our probability of finding it in that area. Okay, we don't know our uncertainty in our momentum. We do know that the product of those two is greater than or equal to h over 4 pi. Now, I'm going to pause this video. I want you to solve for my uncertainty and momentum, and then use that to explain why it is not possible. I'm going to pause the video, and I'll get to there. All right, after doing this work, I ended up with an uncertainty in my momentum of 5.28 times 10 to the negative 20th kilogram meters per second. But that doesn't actually answer the question. So if you want to keep on thinking about why that could lead us to say that it doesn't exist, pause the video and think. I'm about to show you. Well, this is a uncertainty in momentum, or a probability of momentum, and momentum is equal to mv. So that must mean if we are given a mass of the electron, then it must have an uncertainty in its speed. And if we divide the momentum by the mass, we get a speed that is 5.79 times 10 to the 10th meters per second. And that's my uncertainty in velocity, which means that my electron can fluctuate or can have a probability of being up to that amount. And that can't happen because that's greater than the speed of light. That's greater than 3 times 10 to the 8th meters per second. So electrons cannot exist in the nucleus because in order for it to be confined in the nucleus, it has this huge uncertainty in its speed, which is faster than the speed of light, and therefore not possible. These are the fun problems you get to play with. I really like also the energy time ones to show how much energy can something have if you measure within a small enough time duration. Those are also fun problems. Well, that sums up our today's class. So we've looked at the probability of finding a particle in a given position, recognizing that something has a wave function, recognizing that that wave function is also kind of this uncertainty in finding it somewhere. Recognizing that all things have this probability, but they only become really, they have actual implications when they are at the quantum level. Looking at quantum tunneling, recognizing that particles can travel through potential barriers depending on their probability function or their wave function. And then using the idea of this uncertainty in position to show that there's also this uncertainty in momentum, coming up with a relationship for it somehow, and using that to explain both the existence of virtual particles and different applications of the uncertainty principle on electrons or particles. All right. That's all that we have, so I will see you in class.